Hi there, welcome to this video. If you're sitting A-level maths this summer, then this is the video for you. This is actually the third in a series looking at just the pure content, and I did give the questions in this video to my current year 13 pupils who did find them a little bit tricky. So if you are finding the revision hard going, I just thought I'd mention I am running some paid for revision workshops starting on the 13th of May. So it's an hour and a half. If you'd like to sign up and do some revision live online with me, then there's a link in the description and you can just sign up there. There's also a link to an A-level quiz in the description, and that will assess your current grade, so you can have a go at that as well. And also remember that there are timestamps in the description, so if you want to watch a particular question, you can just go directly there. Okay, let's get started with some pure paper questions, and a good way to use this video would be to pause and have a go at the question and then watch my solution. Okay, good luck. This first question is a vectors question. Now, chances are that you've not had much chance to consolidate your knowledge on vectors. It is a relatively small chapter, but it is towards the end of the course. Now, vector questions, you usually find part A is a more straightforward question, so straightforward answer, and then you utilize that information in parts B and C, and that's what we're going to do in this question. So we've got this sketch OAB. We're told that O to A is vector A, so that's A, but we're told O to C, so starting at O is double that, so we're just going to continue that journey and C will be up here, and now O to C is 2O to A. M is the midpoint of AB, so we can put that in. The straight line C and M cuts OB at N. So we need a straight line through M and it's going to cut O to B at N. Now all of B, O to B is the vector B. We've got it there. So our first job is to find C to M. So we can't go directly there. We need to use the vectors A and B. So C to M, if we nose to tail the vectors, we need to go C to A plus A to M. So where that one finishes, that one starts. That's what I mean by nose to tail. Now C to A is easy. That's just minus A because we need to go back through A. Remember, direction is important. But A to M is equal half A to B. So sometimes I'd like to do little journeys on the side and then feed them into what I'm actually trying to do, which is C to M. Now A to B is the reverse vector. To go from A to B, we need to go back down A and then all the way along B. Now we can say minus A plus B, but we usually write that as B minus A. So now we need to feed that in here. So it's plus half of B minus A. Now we just collect like terms. We've got down 1A, down another half A. So altogether we're minus 3 over 2 in the A direction, plus when we multiply the half in, half B. In part B, show that ON is all this thing. We can see that you've got something in front of the A vector and something in front of the B, and we're using this lambda is a scalar constant. So we can see that to get to O to N, it's just going to be some scalar of O to B. So we might call that mu O to B. So it's some fraction of that journey. But here we can see that what we're after is a journey that includes some part of A. So we're not going to go just directly along that baseline. We need to go all the way to C, and then because we are told that CM and then the point N are on a straight line, then it's going to be some lambda of C to M. Now lambda will be bigger than 1 because we need to go past M and then carry on to N. So let's do that journey. O to N is going to be O to C plus lambda C to M. Now O to C is easy. That's 2A plus lambda, and what was CM? We've just found it in our previous question, minus 3 over 2A plus half B. Now what you need to do is collect all the a terms together. So that is 2 minus 3 over 2 lambda in the a direction plus half lambda in the b direction. So that's how we do part B. Now part C says hence prove that O to n and n to b are in this ratio 2 to 1. So O to n is there and then carrying on to n. So this needs to be in the ratio 2 to 1. So what we are looking for is that O to n is 2/3 of O to b. We're going to use this information here and another scalar constant. So we've got one journey O to n here in our previous part B. Another journey O to n is going to be mu of b, so some scalar of b. So what we need to do is compare coefficients. So those journeys are both equivalent. So here the amount of b and the amount of b here must be equal. Half lambda equals mu. So lambda is worth 2 mu. Now also the journey O to n just goes directly along that base there. There's no a involved. So this journey doesn't have any a when we just go directly along. So the actual calculation that we did previously, it's telling us that the 2 minus 3 over 2 lambda must equal 0 because we haven't actually got any a to go straight to O to n. So that's telling us that 2 is equal to 3 over 2 lambda. So 4 over 3 is equal to lambda. So if we put that in here, we're going to get that 4 over 3 is equal to 2 mu. And so 4 over 6 is equal to mu. So mu is equal to 2/3. Now what was mu? Mu was the fraction of b. So we've seen that that is 2/3 of b. So O to n is equal to 2/3 of b. So n to b must equal 1/3 of b because the whole journey is a whole b. So therefore O to n to b is in the ratio 2/3 to 1/3, which is 2 to 1. This next question uses the sign graph to model the depth of the water in a harbour on a particular day in a 24-hour period, and T is the number of hours after midnight. The boat enters the harbour at 6:30, so that is when T is going to be 6.5. It takes 2 hours to load its cargo, and the boat requires a depth to be at least 3.8 before it can leave the harbour. For part A, you're asked to find the depth of the water in the harbour when the boat enters. So that's going to be when T is 6.5. All we need to do is to substitute that in. So it's going to be 30 times 6.5. And if you do that on your calculator, it comes out to be 4.48 meters. And you're doing that just for 1 mark. That's fairly straightforward. But that's getting you into the flow and just getting your head round thinking what 6.5 means and what the height will be when we've entered the harbour. In part B, it's a bit more tricky, and it does say that you shouldn't base your answers purely on graphical methods. It's asking us to find the nearest minute, the earliest time the boat can leave the harbour. But it is a good idea just to get your head round what is going on with the sign graph and how this relates to the depth of the water. So if we put T on our axes instead of X, we're using the sign graph. So there's the sign graph in one period. Now if we put 24 here as T and do 30 times 24, that gives us 720. And this is going to tie in with the idea that the harbour, the depth of the water in the harbour, the tides will come in and out twice in a 24-hour period. So there'll be 2 maximums and 2 minimums. So in the one period we only get to 360, but if you double 360, that's 720. So it means that we are going round twice of the sign rule. sine graph, sorry. And if we want to have the t on the axis, this will be 24. And if I just look at all the places where the sine graph goes through the axis, this will be 6 hours, 12 hours, and 18. Now, the other bits and pieces to transform the graph, this 2 will mean that the graph is going to go up to 2 and down to 2. And then the 5 on the front means that the whole graph is going to shift up 5 places. So that's a translation. So if we draw the graph, and then if I put in the line y equals 5, then it's going to go up to 7, down to 3, up to 7, and down to 3 again. So these places are going to be our time. So we're going to have 6, 12, 18, 24. And what we're trying to do is find the earliest time the boat can leave. Well, it entered at 6:30. So here we go 6:30, so just past 6. This will be our 4.48 that we've just found in part A. So obviously this is on the time when the tide is going out and the water's going down. So we don't know whether 2 hours will pass and there'll be enough time to load the cargo and then we can get out, or whether we'll have to wait till the next time it comes past the 3.8. So 3 would be at the bottom here, so 3.8 is going to be here. So we need to find the times here, but it's going to be after midnight when the boat can leave. So what we need to do is say that 5 plus 2 sine of 30t needs to be bigger than 3.8. And then if we take away 5 and divide by 2, the sine of 30t will have to be bigger than 3.8 minus 5 over 2. And on your calculator, that comes out to be, if we inverse sine, the 30t will have to be bigger than minus 36.9. But when you do inverse sine of that and get this on your calculator, that refers to, on your sine graph, the angle here is going to be minus 36.9. And we want to track that over here. So you can ignore the minus, that just means that we've gone the other way, and we can just add 36.9 to 180 and subtract it. So 30t to get those times in terms of the sine graph is going to be where the angle is 216.9 or 323.1. Now if we divide by 30, t at those times is going to be 7.23 or 10.77. Now obviously if we've arrived at 6:30 and we need to let 2 hours go, that's going to be 7:30, 8:30. So this one's not going to be possible. The tide will go low and we'll have to wait till the next one. So t will have to be the 10.77 hours after midnight. Now that is a decimal, so you need to do 0.77 times 60. So it's going to be 10 hours 46 point something. So I would say it's definitely going to be above the 3.8 by 10:47, and that would be AM. This next question is using the trapezium rule, and I've put how the trapezium rule appears in the formula booklet. So we're approximating the integral by splitting it into trapezia. So when you're at GCSE and you look at trapeziums going this way, these are my parallel sides, and the formula you get on the formula sheet at GCSE is it's half a plus b h. Now a and b are the two parallel sides and h is the distance between them. But when we have our trapeziums going this way, A and B are the vertical parallel sides. They are the y ordinates. So we've got y0, y1, etc. all the way in equal strips to yn. And the distance between them, these trapeziums are lying on their side. This is our h. So you can use this formula here to just divide the interval into the n strips, or you can just look and see that h is the distance between the usually the x coordinates, but in this case we've got t on the x-axis and x on the y-axis. But all we need to do for part A is fill in the table and use the equation to get what x is when t is 6. So x is going to equal 4 times t, which is 6, times e to the minus 1/3 times t, which is 6, and then plus 3. If you do all that on your calculator, out will come 6.248046. We want our answer to 3 decimal places, as the rest of the answers are 6.248. So just 1 mark for doing that. In part B, we're going to approximate and use the trapezium rule. So the area is approximately equal to half h, which is 2 times, now you have to have, it's the 2 y coordinates, but x is on the y-axis, it's one of each of those, so it's 3 plus 5.223 plus 2 lots of all the ones in the middle, 218, plus the one you've just found, and then all that on your calculator comes out to be 49.369, which is 49.37. This is part C of the trapezium rule question, and we're asked to hence find an approximation for this integral. So we can see it's going from 0 to 8, the same, but our original diagram said x is equal to 4t e to the minus 1/3 t plus 3, and we haven't got the plus 3 on the end. So what's happened is, because it's disappeared, the graph will transform and shift down 3 places. So really the graph will be like this, so it's all shifted down, and what will be removed is a rectangle that is a 3 by 8, so that will go shifted down, so we'll just have this shape as our R. So what we need to do is use our previous answer, which was 49.37, and take away a 3 by 8 rectangle, so taking away 24, so our answer will be 25.37. This next question is a differential equation question. We've got a spherical mint of radius 5 placed in the mouth. 4 minutes later, the radius is 3. In a simple model, the rate of decrease of the radius is inversely proportional to the square of the radius. Use the model, and for part A, find an equation linking radius and time. So circle this word rate. As soon as we see the word rate, something is changing with respect to time, and what is changing? It's the radius. So that word rate means that we can write down that dr by dt is proportional to, well, it's inversely proportional, so it's going to be 1 over the square of r. Now we can lose the proportional sign, which is the fish, and write dr over dt is equal to k over r squared. Now we go back to the question. It's saying that when t is equal to 0, r is equal to 5, and when t is equal to 4, r is equal to 3. Now what we're going to do is solve this differential equation and have 2 unknowns and use the information to find it. So how do we solve a differential equation? We need to separate the variables and integrate. That means that you need to take all the r terms to this side so that the dr is in the numerator position, and the dt needs to come up and be in the numerator position on the other side. So we're going to write that it is r squared dr cross multiplying is equal to k dt. Now let's integrate r cubed over 3. Now you would have a plus c, but what we do is integrate the other side and just have one integration constant of the two constants lumped together. Now these are our two constants. We've got c and k to find. So using the first bit of information, when t is equal to 0, we've got r is 5, so 125 over 3 is equal to, when t is 0, the k term there will go out and we'll just get c. So our equation will be r cubed over 3 is equal to kt plus the c, which we've now found is a constant, and then use the second bit of information. When t is 4, r is 3, so 3 cubed, 27 over 3 is equal to 4k plus 125 over 3. So all we need to do is take 125 over 3 off both sides, so move that over, then divide by 4, and your k comes out to be minus 49 over 6. So our equation is that r cubed over 3 is equal to minus 49 over 6t plus 125 over 3. Now it didn't say in terms of t, that would mean make r the subject. It just said find a linking equation, so that would be fine to just leave it like that. In part B, hence find the total time for the mint to completely dissolve. Well, when the mint is dissolved, this is going to mean that r is equal to 0. So we're going to have 0 is equal to minus 49t over 6 plus 125 over 3. Just take that minus term to the other side. 49t over 6 is equal to 125 over 3. If we just cross multiply, that will give us that t is equal to 5.10 minutes. We're in minutes. So what does it say? To the nearest second. So the 0.10 of a minute, we'll have to transfer that into seconds. So 0.1 of a minute is going to be 6 seconds. So this is 5 minutes and 6 seconds. Now in part C, it's saying suggest the limitation of the model. As t gets big, this minus term is going to be bigger than the 125 over 3. So the model would predict that the radius would be negative, which is not going to happen. So that's one limitation. Another one, it doesn't take into account the way people eat the mints. Some people might bite them and then you'd have no radius. So just thinking a little bit about this model being simple and what could happen and the limitations. There would be quite a few that you could have for part C, and part C was just 1 mark. This next question is parametric integration. We've got x and y given parametrically in terms of t. T goes between 0 and pi by 2, so 90 degrees. Show that the area R is given by this integral here. We notice it's dt. So what we need to do parametric integration is go from the x values, which is 0, and then we could do with finding that part there. So we'll need to find that, and then it'll be y dx. So when we integrate with respect to x, that finds us the area. But because y is given parametrically, in order to put y in terms of t and get a dt, we're going to do from 0 to that point there of y in terms of t times dx by dt. So we're going to have to differentiate this, and then times by dt. Now informally, these dt's can cancel, so we will actually just be finding the area with respect to the x-axis. So we'll be using dx because these would cancel. But this is going to allow us to put y in terms of t. We need to multiply by the differential of x, but we also need to have these limits in terms of t. So let's have a go at finding this position here, which is when y is equal to 0. So that would be 5 sine 2t is equal to 0. So that would be sine 2t is equal to 0, 2t is equal to 0 or pi, so t is equal to 0 or pi by 2. So the 0 one is obviously that one there, and then if we put x is equal to 6 sine of pi by 2, pi by 2 is 90, sine 90 is 1, so that's going to equal 6. So that point there is 6. So really we are integrating between 0 and 6 of y dx, and that is equivalent to, in terms of t, the 5 sine 2t times the differential of x dx by dt is equal to 6 cos t. So that would be times 6 cos t. And then we would be doing dt. And now all we need to do is get in our limits. So when x is 0, t is going to be 0. So when x is equal to 0, 6 sine t is equal to 0, so t is equal to 0. And when x is equal to 6, well, we've already done that. We know that the t was pi by 2. Okay, so how are we going to get this here? We just need to use our double angle formulae. So we're going from 0 to pi by 2 of 5. Sine 2t is 2 sine t cos t, and then times 6 cos t dt. And when we sort all that out, we're going from 0 to pi by 2 of 5 times 2 times 6, which is going to be 60. We're going to have sine t cos squared t. So we've done part A. In part 2, we're being asked to hence show the algebraic integration is exactly 20. Now, the exam board have done a show that question and given you what you've got to get in part 1. If you've not been able to get those marks, the exam board is not trying to annoy you, it's trying to give you an answer to work with to then go on and get another 3 marks. So don't give up on a question if you've not been able to get that answer. Use it. Your job is to maximize your marks in the exam. So we've got to integrate between 0 and pi by 2 of this function here with respect to t, and we can spot that it is of the form where you've got f dash x fx. Now we haven't quite got the differential. Cos differentiates to minus sign, but we can compensate when we do the integration for that. But all we need to do is concentrate on this function because the differential will come when we do and look at the reverse chain rule. So if we just look at the cos squared and integrate with respect to the outside function, which is the squared, cos squared t would integrate to add 1 on and divide by the new power. Now, if we differentiate that, the power would come down, cancel with that 3, and we'd get cos squared. That would be differentiating with respect to the outside function, but then we'd need to times by the differential of the inside. Now, that's already there, but we just need a minus, and then the 60 also just needs to join in. So that is our integration from 0 to pi by 2, which is equal to minus 20 cos cubed t. So this is looking good because at least we've got a 20. So now we're feeding our limits. If you have a little think about your cos graph, when cos is 90 pi by 2, we get 0. So that is going to be 0 when we put in our first limit, and then when the angle is 0, the cos of 0 is 1, so that will be minus 20, and then we'll have minus and a minus, and that will give us the 20 that we want. This is part B of the same parametric equation question. We've got the curve being used to model the profile of a small dam. The wall of the dam here, stopping the water going any further, is 4.2 meters high. X and Y are in meters. There's a horizontal walkway of width mn across the top of the dam here, and our job is to calculate the width of that walkway. So we really want the x coordinates here and here because we're going to take them away from each other to find how wide that walkway is. So our parametric equations told us that y is equal to 5 sine 2t, and we're being told that we want y to be 4.2. So if we just equate that to 4.2 and start to solve for t, then sine 2t will equal 4.2 divided by 5. And then if you inverse sine that, remember you have to be in radians. Whenever you're doing anything with calculus, you need to be in radians. But inverse sine of the 4.2 over 5 gives us that 2t is 0.997. Now that's what our calculator will give us, but remember there'll be two answers from our sine graph. Our calculator has given us this value. We need to do pi minus to get the other one, which will be 2.144, and dividing by 2 will give us our t's, 0.4985 or 1.0722. Now what we need to do is not find t's, we need to find the x coordinates. So the other parametric equation was that x is equal to 6 sine t. So we're just going to put each of these in. X is going to equal 6 times the sine of 0.4985, which is equal to 2.869. So that will be that one there, the first one. And then if we put the other one in, x is equal to 6 times sine of 1.0722. And on your calculator, that comes out to be 5.270. So the width of the walkway, MN, is equal to 5.270 minus the 2.869, which comes out to be 2.40. And that will be in meters. This next question is a numerical methods question, and we use numerical methods when we can't solve algebraically to look for where an equation has a root. An equation has a root where it passes through the x-axis. So if there is a root and the curve is continuous, either side of that root, and we're being asked to look in the interval 3.5 and 4, before the root it'll be negative and after the root it'll be positive, or vice versa, because what we're looking for is just a change of sign. So if we do f of 3.5, so that is put in when x is 3.5 just into our equation, that turns out to be on your calculators minus 4.8. And then if we do f of 4, the other side of the root, that comes out to be 3.1. So we have got a change of sign, and we need to say the function is continuous, and then those new updates of the textbook, we should be also maybe saying therefore at least one root. Now in part B, we're being asked to apply the Newton-Raphson procedure. So you get that on in the formula book, that the next one along when we're looking for a root is the previous one minus f of that over f dash. Now we're not being asked to differentiate because it actually gives us what these values are. A student takes 4 as its first approximation, so that's going to be our xn. It's asking us just to find the second one, so all we need to do is do 4 minus f of 4, which it's told us is 3.099. I got 3.1 there just to show that it was a change of sign, but 3.099 is a better one to use, and it's what the question is given us, divided by 16.67. If you do that on your calculator, you will get 3.81. Now in part C, it says show that alpha, and we've got a better approximation, 3.881, is the only root of the equation. Now the equation was the ln of 2x minus 5 plus 2x squared minus 30, and we are looking for where that is equal to 0. So what we can do is say that the ln of 2x minus 5 must equal, taking this term to the other side, will be minus 2x squared plus 30. And to show that there's only one root, we could graph both of those, and there will be only one place where they intersect. So looking at the quadratic equation first, it's a negative quadratic, so that's going to be this shape. It's going to have the y-axis as a line of symmetry, and it's just going to be shifted 30 places up and be a little bit steeper with that 2 on the front. So it's going to go something like that. And then plotting the ln graph. Ln graphs are the inverse of e to the x, and that goes through 1. So the ln graph goes through there at 1. It has the y-axis as an asymptote, so that is going to be where this is equal to 0. So we just do 2x minus 5 is equal to 0. X is going to be 5 over 2. So that is going to be our asymptote here at x equals 5 over 2, and the ln graph is going to come up and go like that. So from the graph we can see that there's only one point of intersection, and that would be how we will show that there's only one root. Last question then, and this is another limit of a sum which is going to be the same as if we integrate. So as that dx tends towards 0, we're just integrating and adding up all the strips. So this is the same as the integral between 4 and 9. Root x, we're going to write it as x to the half, and we're going to integrate with respect to x. So this is really straightforward now. Just got to recognize that that's what it's asking us to do. So adding 1 on to a half will be 3 over 2. Dividing by the new power, when we divide by 3 over 2, it's the same as timesing by 2/3. And we're going between 4 and 9. So sub 9 in. This 2 here will mean the square root of 9, which is 3, and then 3 cubed is 27. So it's going to be 2/3 times 27. Take away, when we put 4 in, the square root of 4 is 2. 2 cubed is 8. So it's 2/3 times 8, which is going to be 54 over 3 minus 16 over 3, which is 38 over 3. Thank you so much for watching. Hopefully you found the content of this video useful and helpful, and your revision is going well. I'm going to keep making videos, so keep an eye out on the channel. Sign up in the description if you'd like to join me on an online revision course, and I will see you on the next one.